Ma'am, if you have to test any screen sharing and things. Digambar sir, can we start?
If you can see my screen.
Okay, ma'am.
Yes,
Hello.
ma'am. Your screen is visible, ma'am. Yeah.
Okay.
We'll wait for 2 minutes, ma'am. After that, we'll start. Our
Sure.
scheduled time is at 6. So Am I audible to all?
Yes, sir, you are audible.
Okay. Good evening, all. So today is our second day of FDP on Geo-AI innovations in AI for improved spatial data processing, organized by Ramravadi Institute of Technology, DY Patil University, Navi Mumbai. This one is the ATAL online 1 week approved FDP. So today we have a speaker, eminent speaker, Dr. Ujwala Bangale Chaudhary is a research fellow at London, South Bank University, London, UK, specializing in high performance computing. She earned her PhD from IIT Bombay in 2018, where she focused on the knowledge discovery from Earth observation data, HPC on multi-core systems, and geographical information system, GIS. Her research during this period contributed significantly to the integration of advanced computing techniques in geospatial data analysis. Dr. Bangale's research interest extends across the multiple domains, including data exploration, big data analytics, with the emphasis on applying high performance computing to solve the complex computational problems. With over 16 years of academic experience and 2 years of industry experience, Dr. Bangale has built a robust career combining the teaching, research, and practical applications in her field. She has authored numerous research papers in reputed journals and conferences. Her diverse expertise includes the working on the interdisciplinary projects that leverage HPC to enhance the data processing and decision making. So, with this small introduction of ma'am, so I would request ma'am to continue with your expertise lecture. I welcome you, ma'am. It's over to you.
Thank you, sir. Thanks a lot for your kind words. I'm sharing my. Can you see my slides now?
Yes, ma'am. It's visible now.
Yes, yes.
Yeah. Okay. Okay. So good evening, everyone, and thanks a lot, sir, for giving me this opportunity. Thanks to the RIT Institute for this opportunity. So my today's talk will be on the spatial data exploration analysis using the high performance computing platforms. So why do we need a high performance computing platforms for remote sensing data or remote sensing? Um, can say I mean the data captured by the uh, spaceborne or airborne sensors. The reason is, I mean, just like since the big data term is quite popular nowadays, so remote sensing data is also termed as a big data because it satisfies all the criterias we apply to classify any data as a big data. The first criteria is variety of the remote sensing data. As we can see that the remote sensing data nowadays can be captured by, I mean, it's spaceborne, airborne, but then nowadays the drones are very much popular for capturing the data. So at some point of time, we may need to integrate the data captured from the Earth observer sensors, then airborne sensors or the drone sensors. So we may need to integrate the data captured by this variety of sources to conclude certain decisions. So yes, so a variety of data is there. Then the remote sensing data is quite massive because the data is with a high spatial resolution. Say some of the images of very high spatial resolutions, maybe in terms of 28,000 by 28,000, the one which I had processed. So that kind of spatial resolution is there. Then again, the spectral resolution. So the hyperspectral data, sometimes the number of spectra captured are around 255 or something like that. So you can imagine the volume of data or the massiveness of the data captured by these hyperspectral sensors. Then the temporal resolution is another reason. So the data captured with a high frequency. So nowadays the sensors are sorry, sensors are capable of capturing the data relatively with a high frequency. So there's a massive data the remote sensing can generate. And then the another characteristics is the velocity. Okay, so it's basically in terms of data rate to generate data or to transfer the data, say maybe from the satellite to the earth centers, the earth stations which collects the data. So the packets, the downlink capacity is nowadays quite high. So again, a huge amount of data get populated at the ground stations. Then again, the computationally expensive algorithms, as the remote sensing, the nature is quite, we have seen the variety, like the spectral features are there, there are spatial features. So the algorithms are there which combines the spatial features as well as spectral features, the algorithms like spectral angle mappers. And so those are quite expensive to compute on the huge amount of data. So it requires a huge amount of time to process this data, and eventually lacking immediate response to the end users or to the developers. Even to, I mean, we usually have the tendency to tune the parameters, change parameters. We want to see the results immediately, but then due to this high volume and then computationally expensive algorithms, it becomes difficult to check for the results quickly. Okay, so to handle these challenges or to overcome these limitations, what we have with us is the high performance computing power. Okay, so high performance computing enablers for the spatial data exploration. Broadly, I would say two different enablers are there. First one is a parallel processing or parallel computing, which helps us to perform the task in parallel. And then another main is memory scaling. So we can store the data, I mean, huge amount of data by scaling the memory. So here we would be focusing more mainly on the parallel computing or parallel processing aspect. So parallel processing is it's basically we are processing the data or the operations in parallel using multiple processors or nodes to speed up the computation. Okay. So this parallelization, we have three options possible. One is a data parallelization where we can perform the same operation on each data element. Okay, so data parallelism is where we divide our data across multiple cores or nodes, and then we usually performs the same operation on that data. So that's a data parallelism. Then we also have that pipelining or streaming, which is usually provided by the typical sequential unit CPUs. So that possibility is also there, where we can streamline the multiple operations and can gain the performance. And then task parallelism, where we can divide um, multiple, I mean, one job we could divide into multiple tasks, sub operations or sub process we can say, and then each task we can give it to one processor or a core in order to execute it. So mainly we would be focusing on the data parallelism and then the task parallelism. So data parallelism, as I said, where data we distribute across multiple cores, and then usually we perform the same operation on that data, and at other end there might be different tasks or different operations, and then we may execute those tasks on same data or maybe on different data. So that's the task parallelism. Okay. And then there is another important aspects in this parallel computing, which is the granularity, which is nothing but the qualitative measure of a ratio of computation to the communication. So when we say that we perform the data parallelism or a task parallelism, always we have to do some kind of communication, some kind of data transfer is involved, because we say that we execute it on multiple processors or on multiple nodes. So obviously there is one task that is moving the data from one location to another location, maybe from the central location to the multiple processors, where each processor would be then capable of processing that data. Okay, so that data transfer, rather communication, I would say that's a data transfer cost which is involved here. Okay, so this data parallelism, basically if we divide into two types based on the granularity, that is a fine grained parallelism and then coarse grain. So fine grain is it's basically we are considering a very small size of a data, small set of a data, and then we again perform a small computation on that data. Okay, so the if we talk in terms of images, then the fine grain is nothing but at pixel level, individual pixel. So we can even do the distribution at pixel level. So if I have the image of 124 by 1024 by 1024, then each of my core would be holding one pixel, and then the operation will be performed on that pixel, all the pixels in parallel. So that's the fine grained parallelism. Okay, we'll see the example later. But here what I want to discuss, because here this is important aspect, that what kind of parallelism you are looking in your operations or in your methodology, and which is very much dependent on what kind of algorithms you run, and then what kind of hardware or infrastructure is available with you. That matters a lot, right? So fine grained, as I said, that for image processing, it is usually at the pixel level, and relatively for the small amount of computation. But then, of course, the data communication, the data transfer is involved into that, which is quite costly. So always the granular, the low computation to communication ratio is there. So that means the lower performance, you could say, the lower speed gain. Okay. So because the communication cost a lot in such kind of cases. But then if computation is too complex, okay, and then if it's a massive amount of data, then of course we can observe the good performance. This I will demonstrate with some examples. So hope you, the concept of fine grained parallelism is quite clear. Then the another one is a coarse grain parallelism. The coarse grain is now against that of the fine grain. We would be giving a large amount of computation work, probably on good amount of data. Okay, so here the large computation would be given to the nodes or multiple processors. Probably we may observe the high computation to communication ratio. Okay, and then here for such kind of a task, we can see a good performance, good speed up can be observed. But then the benefit of fine grain is we can do a proper balancing of load. As I said, that if you go to the lowest level of granularity, that is the pixel level, if we spread pixel to each core, then there is a proper balancing. Every core has one pixel to process, so exact balancing of a data. But then if we are going for the coarser grain, of course there will not be that kind of load balancing. But then yes, you can see the performance over there. Okay. Now the another one which I said, that the memory scaling. So nowadays a lot of specialized storage and access devices are there to handle your huge amount of data, which usually the single device is not capable of. So to enable this parallel computing, what kind of infrastructure available with us, or what resources which we can use are, we can use the cluster computing, basically the nodes or the systems which has the same you can say architecture, okay, the processors or the operating system. So whatever the hardware and softwares required, so that could be similar. So that's a cluster. It can be the heterogeneous computing as well, distributed heterogeneous, which when say on cloud, we may use multiple systems with different configuration to achieve the high performance. And then there are specialized devices like the field programmable gate array FPGA, and which is also programmable, so that can be used. And then the one which I prefer is the GPU, the general purpose graphics processing unit. Okay, again a specialized hardware by NVIDIA. So these are the high performance computing technologies which we can use for big data processing usually. And then yes, that edge computing in the sense where if you need to process the data where it's get generated, or at the source of the data, just to provide immediate responses to the end user, say providing responses to the farms based on their depending on what are the parameters captured at maybe the soil moisture, temperature, or some other parameters along with the earth observation data. Probably we can deploy some kind of edge computing technologies like the NVIDIA Jetson board. Okay, the black one is a Jetson board with all the capabilities. I mean, kind of you can attach multiple resources as per your requirement, and then this board holding the NVIDIA processor capable of processing the task or your algorithm in parallel, and can be able to generate the results which the farmers can consume. So edge computing nowadays is quite popular. So yes, you have multiple devices. We can use the Raspberry Pi as one alternative, or the Google Coral is another alternative for this edge computing. Okay, so yes, it's basically the high performance devices again, which we can use at the source. So as I said that I would be focusing mainly on the GPU. So I mean, this is my favorite diagram, quite easy to understand nowadays. If you will see the architecture of a GPU, it comes quite complex, but then yeah, this one is quite simpler. And what the GPU consists of, because the demonstration of this fine grain and then the other one, the coarser grain, yeah, I'm using the MPI platform for the same. But then just to understand that what makes the data process in parallel, it's better to understand the architecture of the device itself. Okay, so this is a typical GPU architecture, very a simple configuration where we have multi-processors. Okay, these multiprocessors nowadays referred as a streaming multiprocessors SM, and then every multiprocessors has multiple processors. You can see the processor 1 till processor n. So multiple processors are there, and then all those processors works on only a single instruction unit. So you give only single instruction to all the processors. So all the processors basically execute the same task, and what the local memory holds is nothing but the data which you want to process. So the local memory holds the data which you want to process, and there is only one instruction unit which gives the task or the operation you want to perform on this data. So all the processors perform the same operation on the data. Okay, so this particular architecture, we refer it as a single instruction multiple data architecture. So the GPU belongs to this particular category, single instruction multiple data. But then this enables you to process the data parallelism. Okay, so here you can process the multiple data in parallel. So this is architecture very much suitable for the data parallelism. Okay, but then yeah, extending further, GPU is not only restricted itself for this data parallelism, but then yes, it can handle the MIMD as well, multiple instruction, multiple data, and then the task level parallelism as well. Okay, so whenever the processor has to work on the local data or their own data assigned, which usually resides at the local memory, something which needs to be shared by multiple processors, then it gets stored at the shared memory. Some data which is need to be shared across multiple multiprocessor, that usually stored at a global memory. So that kind of memory hierarchy is there for the GPU, and that's why it enables us to perform different kinds of architecture we talk theoretically. So all these kind of implementations are very much feasible on the GPU, like SIMD, MIMD. Those things are feasible on GPU nowadays. So when considering the architecture, now we can easily say that how the GPU is supporting or suitable for the image processing, not only for remote processing, but for all for remote sensing data, but for all the image processing, the GPU architecture is very much suitable. The first thing is it supports the data parallelism, as we have seen that the local memory which holds the data. So every core would be holding its own data, and same operations get performed on all data. So we get the data parallelism over there. Okay, and then since it's a parallel processing, the image processing computations, which usually are expensive because of the high resolution, since it avails the parallel processing, it's very much the GPU is very much candidate to be used for the to achieve the high performance. And then just the image data format is quite suitable for the data parallelism concept. Okay, because image we can really, we can map it as a matrix, can handle it on GPU, and can manipulate it. So it's quite easy to manipulate in terms of a matrix like XY. So that's how we can organize the threads and can work on the GPU. Okay. And then yes, another important characteristics of the image processing algorithm, that usually we perform the same operation on each pixel, right? I mean, you consider any operation, like say you consider the convolution, or say you are looking for some kind of neighboring operation. So usually we end up processing the same operation on all the pixels. So this GPU architecture is really quite suitable for this kind of operations. Okay, so we say that GPU architecture is complementary to the image processing algorithms, and we are observing that now, even if you consider the standard libraries for analysis, say PyTorch or any of, so it has standard support of CUDA, which is the programming environment for the GPU. So that's how the high performance get enabled for those. Otherwise, if you consider the current models available in the market, having say 256 layers and all, so I mean it's the single CPU or single system definitely is not capable of holding that kind of can say extensive operations. Okay, so or it will take months and months to process to perform that complex operations on a huge amount of data. Okay, so yes, we require the high performance computing to handle this data. Okay. Now we look at the operations. Okay, usually, I mean, I'm talking about the image only, the remote sensing, or for that matter, you can consider any other image as well. But then the typical tasks or the operations which we perform on the image of say identifying the edges, segmenting the data, like that's it. I mean, segmentation, and reducing the noise, enhancement, some kind of transformations, rotation, resizing. Okay, so I have listed few here, like morphological operations, maybe the erosion, dilation, closing, opening. So all these operations, the convolution. So morphological, even if you say one pixel, whatever operation we perform on one pixel, the same operations we usually perform on all the pixels, isn't it? So this is applicable for all the operations which you see here. Convolution works the same way. It's neighboring. Basically, what we can see over here, all usually the neighboring operations or something that the same operations we will be performing on all the data. Okay, and that's why this makes it more suitable for executing on GPU. Then proximity computation, like convolution is a base candidate. The models which we consider nowadays, like Gen AI, all it's a convolution. If you consider that for image processing, then what is there at core is nothing but the convolution kernels, right? So these tasks, even the proximity calculation, the proximity matrix, like the distance calculations among two different objects or two different elements. So all these different kinds of operations which I have listed over here, the band ratioing, which is something, we consider several bands from the image, and then we calculate the ratio out of that, select the bands which are appropriate for highlighting the specific kind of elements from the image, and then we calculate the ratio out of that. So that's a band ratioing, basically usually used in remote sensing images. So these kind of operations we can easily perform using this GPU. Okay, and we can achieve a good, excellent performance for in terms of speed up. So let us look at some case studies. So the first one, what are the operations? The case studies I would be explaining with respect to the operations which I'm talking about, but then just to cover the basics. So this one is about the oil spill, where the oil spreads over the sea surface, and then it impacts um, the this marine and coastal life badly. It has adverse effects on the wildlife species, local industry, fisheries, and many other sectors. So, and then nowadays it's observed that this oil spill happens across several countries frequently, and there's a need to look into it seriously. So, what is the one observation is, usually that oil spill formulates a specific shape over the sea surface, and some kind of characteristics gets generated which help us to identify it as a oil spill. So the methodology which is considered here is this is the data considered here is the Landsat 7, and then both the spectral data and spatial data. The both spectral properties and spatial properties of that data are considered for processing. The spectral properties is basically to calculate the band ratio, to calculate the oil spill index, and then spatial, based on the spatial properties, the morphological attribute profiles are calculated. So in order to calculate that morphological attribute profiles, first the connected components are identified, and then for each of these morphological attributes, again we can bifurcate into physical, some of the attributes which would be representative physical characteristics like gray mean, and then the standard deviation, and then some represents the geometry of the shapes like elongation, solidity, sleek complexity, and orientation. And then there is a cascaded filtering applied on that to identify the oil spill. And this entire methodology is implemented on the GPU. Also, with the MPI platform, which is a cluster computing platform for high performance computing. So now, earlier I talked about the fine grained parallelism, right? Fine grain, as I said, at a pixel level, we on each of the pixels get processed parallelly. So the band ratio implementation on HPC, you can see the code. It's quite similar to that of C, so easy to understand. This CUDA has support to many languages, so C is one of them. So I have used C CUDA for this implementation. So the CPU version, you can see here that, I mean, the two for loops which was usually we require to iterate or to go through each of the pixels from that image. So always the number of rows into number of columns is a complex computational complexity for that. But when you see the CUDA representation, the band ratio calculation on the GPU, you will not see any for loop. The reason is the image is the pixels are given to each of the core. So each core is working on the data which is locally stored, and so each of the pixel is part of the local memory of that core, and that's why it is processing it in. So there is no need of for loop, right? Each core has its own pixel. Okay, so maybe 3 pixels at one particular core would be holding, and it would be processing thread, basically, I would say, not core. In terms of GPU, it would be the thread. So it is using, I mean, each thread is executing this task in parallel, so there is no for loop. But then, yeah, you can check the constraint so that it should not go out of index for the rows and columns. So the computation complexity for this simple operation, okay, fine grained, okay, where we are doing the division, pixel wise division, okay, so that fine grained parallelism is been done here. So the computational complexity of order of rows into columns is straightway going to certain constant. Yeah, so that's how we achieve the band you speed up over this band ratio. But then, as I said, that the communication cost comes into picture. Okay, so just to give you that how much is a communication cost. Okay, communication cost, I'll repeat again that it's nothing but the cost involved in, or the time. Say cost is nothing, we will talk in terms of time. So the time required to communicate the data. Okay, so it's basically the data transfer cost. Okay, so if you'll see that red line, okay, this red line, it represents the only function execution, only that band ratio computation. Okay, so for this size of image, say 18,432 by 18,432, the
Dancer.
time taken for this size is 0.
Ma'am, you are not audible. Ma'am, your speaker is mute. Ma'am, your speaker is mute.
Ma'am, you are on mute. Hello.
It was on mute. I'm not sure.
Yes, ma'am, go ahead.
Yeah,
Yeah, ma'am. Now audible.
since how long it was on mute? I don't have any idea.
No. Only 30 seconds.
Okay, no worries. Okay, so yeah, what I was telling that, I mean, we are what we are looking at as a fine grain parallelism. So what happens in fine grain parallelism? The computation we perform is very less. Okay, and then we we consider a small unit of data as well, like say pixel level computation we are performing. So what is happening is that pixel level, the computation time is only 0.0167. Okay, that's the only computation time, but we require to move the data to the GPU. That's a communication cost. So the communication cost involved is one, I mean, including the communication cost, the execution, I mean, the total time taken by GPU is 1.03. So here we can clearly see the communication cost is 64 times more than that of a computation. So, but still, if you consider the CPU time, CPU took around 6.88 seconds to achieve the same thing. Okay, so of course, overall performance is 6 times greater than what the CPU achieves. Okay, but because of the communication cost, it is just 6 times greater than what the CPU does. Okay, but then if you just consider only the computation cost over CPU cost, then it is around 412 times faster than CPU. Okay, so that is what, I mean, we need to consider that here, even after considering the data transfer cost, I am still achieving the speed up over this CPU. Okay, but then for that also I need to handle some kind of optimization while doing the data transfer. So um, that's the pinned memory transfer. Okay, even in PyTorch you might have seen the option of pinned memory. So I insist you that whenever you will get that particular I mean, whenever you have the chance of using GPU, please enable the pinned memory, because pinned memory does the faster transfer. It's like on the local system, on the CPU, you are allotting some memory, okay, to store the data, and then that data we move on the GPU. That's what is a pinned memory transfer. Okay, which is obviously faster than the there's some background noise. Okay, so image processing, image size. If you increase the image size, then you can see that unpinned memory transfer, it takes a lot of time to transfer the data, whereas pinned memory, yes, you are saving a lot on transfer time. Okay, and this particular behavior, what you can see, it's using pinned memory transfer, so you are achieving the speed up of 6 over the CPU. But if it's not pinned memory, then you will not get any speed up. So you have to be very much careful about how much of data you are transferring, and is it really worth using the HPC where huge amount of transfer and then low computation is there. So then it won't be beneficial. Hope you understand this kind of, I mean, concept what I tried to explain here. So this is a fine grain. This is example of fine grain. The another, yeah, this one is again the spectral kind of analysis on the remote sensing data. Yeah, the another one, yeah, some results have been discussed here, but we'll not go in detail. This is another example of morphological operations, but nowadays there are standard libraries available for these morphological operations, which you can readily use in your code. So I'm just skipping this as well. But then, yeah, again, if you talk in terms of performance, you get a huge performance even with the data transfer. Say, yeah, with the data transfer, you are getting 220 times faster than your CPU for morphological basic operations. So this one has been done for dilations, but we know that, I mean, closing, opening, all this is nothing but then cascading those dilations and erosion, I mean, these kind of operations in sequence. Okay, so for single operation, if you can get a performance of 220, you can just imagine that how much of performance you could get for those cascaded operations like closing, opening. Okay, the another one is the coarse grained parallelism. Okay, So coarse grain, for this I have used a cluster computing. So that's the uh, MPI based. Now it's not GPU, but it's the MPI, message passing interface on cluster. So multiple nodes are being used. Okay, so here what is basically done is, as I said, that for computing the morphological attribute profile, we identified the connected components, and for each of the connected components, we have identified some characteristics like gray mean, sleek, complexity, orientation, solidity, elongation. So what has been done here, that these kind of features are been extracted by dividing the number of connected components across all the nodes or cores, we'll say. Okay, so we try to balance the load by manually taking care of giving equal number of components, connected components to each of the node, and then each node would have computed the features or extracted the features, and then uh, the features are combined together, okay, by the root process. So this is the one approach where the MPI is being used for the feature extraction. But moving ahead, what has been done now, this is MPI is based on the cluster computing. Okay, so message passing interface is the environment which allows us to process the task in parallel across multiple nodes which are on the same cluster. Now the next step of achieving the more higher performance is a multi-level parallelism, where what has been done, that the root process, okay, on the MPI platform, the root process has distributed the task to multiple cores, to the multiple nodes on the cluster, and further each cluster, each not cluster, each node has used the GPU cores to execute the features. For example, for calculating this elongation and then solidity, and so we had constructed the convexal around each of the components. So starting from calculating the convexal and then major minor axis, everything has been done on the GPU. Even for the computing the gray mean and standard deviation, though not possible to perform the entire operation on GPU, but then, yeah, the simple one, like what we require is summing all the elements just to calculate the average, okay, the mean. So summing all the elements, sum up of all elements have been done on the GPU. So some of the tasks which can be done on the GPU are done on GPU, and then maybe for calculating the actual standard deviation, that can be done on CPU. Okay, so that kind of uh, multi-level parallelism is achieved using combining those, I mean, both MPI platform and then GPU platform. Okay, so uh, here is the performance of this morphological attribute profile on multi-level parallelism. Okay, well, since this particular uh, methodology, it involved a lot of sequential tasks, so the overall gain is not that good, but still better than the CPU, that is at least 11 times faster than the CPU. Okay, so I mean, if you consider, so now we, since it's an MPI interface, so there were multiple cores available, say 8. So the experiment is conducted considering the different number of cores, like considering 8 cores, then 16, then 32, 48, and 64. And along with that, the GPU, K40 GPU, which has around 2440 CUDA cores. So with this configuration, the entire map process, it took around 10.2 minutes with number of components, connected components as 33,638. So for these many components, the execution is done in 10 minutes, whereas the CPU, 8 CPUs, and with the GPU, it took around 88 minutes. So that's how the difference in performance if you increase the number of CPU cores as well, okay, or the MPI parallelism. So if you have a good amount of cores or the CPUs, then of course the MPI, the message passing interface, okay, that is very much beneficial because a lot of tasks are sequential. I mean, what I experience is a lot of tasks are sequential in this process, and then we need to move back to the CPU and then perform the task on GPU. But what if I had 128 cores available with me for processing this? Then obviously whatever speed I would have gained with the CPU and GPU, the same speed I would have gained with only with the help of 128 CPU cores. So yes, it's not about CPU GPU, but then yeah, I mean, GPU is definitely a good candidate when we can do a data parallelism wherever the tasks are quite independent. But if we require some kind of synchronization at certain point, then and if it's required very frequently, then GPU may not be the good candidate. CPU is better for sequential. And then if it has lot many cores available, of course, you will get good speed up or that. So this is about result validation. I don't think we should discuss it more. I just give you the brief. That's the result features we observe for this morphological attribute profile. Those are evaluated using the thematic as well as the geometric accuracy. Geometric accuracy because we are talking in terms of shape and geometrical characteristics. So evaluation should be according. So the geometric accuracy is also evaluated by means of some measures like over segmentation, under segmentation, edge location, shape errors. So these errors are being calculated. Okay, so this is about the oil spill thing, and another case study on the earthquake damage detection on the Haiti earthquake. So you can see the image size around 29,262 into 25,900. So basically a huge amount of or the very high spatial resolution you can see here in this diagram, the one small dot which has been enlarged over here, the same location with enlarged here, where we can see that the data before damage and after damage. Okay, so you can imagine the spatial resolution of this image, and since it's not worth to process single image, since we have to compute, I mean, look for the change detection, we would be considering the temporal data. So that is at least before damage, after damage. So huge amount of data is involved into that. So yes, so GPUs or similar HPC platforms are essential. So here the methodology applied is the SIF scale invariant feature extraction. So the SIF features are been extracted. So there are two important operations which we perform on this SIF. Okay, say the difference of Gaussian, where we calculate the proximity matrix, and then convolution operation is there because we convolve at each of the epoch. We keep on convolving, and then we calculate the difference of Gaussians, and then we detect the extremas. Okay, so these are the major steps belongs to the SIFT. So these tasks have been performed on CPU and GPU, and you can see the performance gain. Now again, I'll say that the standard functions are available for this convolution. We need not have to code it, but then yeah, but just in terms of speed, you can see that yeah, there is one more thing. Like if you keep on increasing the size of a data, you will see increase in the performance, right? So for thousand by thousand image, the speed was around 1.47 speed up, and for 15,000 by 15,000, the speed up was around 57 times faster than the CPU version. And then you can see for each of the operation, like say for convolution kernel, you are getting 57 times speed up. For difference of Gaussian, you'll get the speed up of around 15. For extrema detection, it is around 35. So a huge amount of speed up we can observe by performing this kind of typical task. That's what I mean, for images, the convolution, then proximity matrix calculation, the difference of Gaussian. So these are certain tasks which you usually perform, similar kind of tasks we perform. So we can really achieve good speed up over there. So for proximity also, you will see that if you increase the size along with the 128 dimension, so you will see the proximity matrix calculation, it's around 586 times faster than the sequential one. Okay, you can see the speed up curves. So the blue one is the GPU time, which always remain constant, is stable, and whereas the CPU time, it's very much dependent on the size of the data, okay, data dimensions or the image size. So I mean, as the image size or the dimensions increases, the CPU time increases, whereas the GPU, it almost remains constant. Okay? So you achieve a huge speed up or such kind of operations like proximity calculations. And but yeah, of course, there are some operations where the performance you'll observe will be consistent, won't be changing. For example, minimum value extraction. So there is a speed up over sequential, but then it's constant. No much. I mean, no much. It's nothing to do in this kind of particular operations, right? So it's same for all these things. Yeah, the another methodology applied on earthquake data, okay, captured from the Haiti earthquake. So some first row is it represents the undamaged building considered for training, and then another one with the damaged, and then this kind of convolution neural network model has been applied, okay, with the two classes, whether it's a damaged or undamaged, okay, and then the performance is evaluated considering the different architectures and distribution of data, CPU plus GPU, CPU plus tensor processing unit. So that variations been done. We can see that always compared to the sequential or the CPU or the GPU always gains more performance. And if you have the distribution optimized, then the GPU may gain more than the TPU. So yeah, variations you can see over here over the speed up. Okay, so from this I would like to conclude that the HPC platforms which are available for the spatial data explorations allows the research and analysts to tackle a large amount of this remote sensing massive data to handle the computationally intensive and expensive operations, which requires a huge amount of storage as well. And then we can achieve good speed up or all the commonly used primitive operations like the convolutions, the proximity, the morphology. You can see the speed up over each one as compared to the sequential one. And in addition to that, GPUs, if you say that the interface is already enabled with now. Currently, I'm just talking about the remote sensing imagery, okay? But then another important geospatial data exploration is related with the vector data as well, which we handle using the PostGIS and the other tools like QGIS or GRASS. But fortunately, all these tools like GRASS, then QGIS, even the PostGIS has support of GPU. So we can enable the GPU, and even for the raster data processing for executing the queries like, uh, I mean, whatever the SQL like queries we do in post GIS, for executing those kind of queries for all these operations like across or in of all those queries, there is a support of GPU. So this can be used even. Um, we have this interface enabled with MongoDB and such kind of NoSQL platforms. So we can use. I mean, if anyone working on the the vector data, then they can even take the benefit of this high performance computing, which is already been integrated. You have to just enable the interface and it will work for you. I mean, the query, without you specify anything, automatically the query will get executed on GPU if you have the GPU available on your system. So you will definitely gain a high performance for executing the tasks which otherwise take a lot of time on the CPU. Okay, so yeah, that's it from my end. Thank you for listening, and please let me know if you have any queries. Hello, any queries?
Uh, Thank you very much, ma'am, for your nice
Hello,
talk
ma'am.
on this GPU. Yeah, go ahead, sir.
Ma'am, what is the input data type for remote sensing image processing for GPU processing?
Sorry, what?
What is the data input data type for remote sensing data?
Yeah, so it's what I had considered it as. The image is treated as I said, that I consider it as a matrix itself. Okay, because it's a C, so I need to treat it as a matrix. Though the threads I mean, in terms of threads, we represent it as XY, so we handle it as a matrix only on GPU, right?
Okay, okay. Means that the remote sensing data are converted into the matrix format.
Yeah, I mean, it's an image, so we consider image as a matrix. So we treat it as a matrix.
Okay, because in remote sensing data, the image format is very different na,
TIFF,
as
yeah,
compared
yeah,
to
it's a TIFF images, depends like GeoTIFF and all that. But then ultimately, um, uh, even if I consider it as multiple spectras like band one, band two, band three, I will treat it as three different images. Each image I will treat it as a matrix. The representation is a matrix only.
okay, okay. I mean, another question is that how you calculate the oil spill index?
Yeah, equation which I had shown. So three bands are considered.
Mhm.
Let me share you that screen. Yeah, so can you say it's a band three, band one, and band two? I think band two, three,
Okay.
and one. So it's basically the bands which where by manipulating it's the band selection, it varies, right? If I have to identify the cloud, I would be selecting some different bands. If I have to identify the oil, I would be selecting any bands which are, I mean, which will uniquely give me the oil characteristics. Or if I'm doing it for the NDVI is a commonly known that normalized vegetation index. So there, I mean, it varies. I mean, what you are in what region you is of your interest. Okay, so accordingly you would be selecting the band. So this information, if you Google, like for NDVI, there are a standard set of bands for that specific sensors. Okay, for multispectral, those bands would be responsible, say, in that particular spectra range. So those are responsible for characterizing that particular element. Okay, whether it's a oil or a soil or a vegetation or cloud, anything.
Means by selecting individual band and calculating
Yeah,
parameters.
the ratio. Yeah, I mean, what kind of ratio? Now, this particular one is having a simple operation, like it's just um, uh, one dividing by another, and then the another is at the numerator. There is simply a division of band 2 and band 1. Okay, numerator is just band 3. So, but then that equation varies for each of the index you are interested in. Okay, that, I mean, there are standard spectras where you can use those spectra for computing that particular element or identifying that particular element. As I said, for ND, where there is separate set of bands, and then that operation you would be performing across those bands to calculate the representative property.
Okay, okay. Means some of the characters like need to extract some mean data or some standard deviation
Yeah.
like this.
Yeah, so whatever is there, whatever I selected for oil spill, those won't work for water index. Okay, that would be different.
Okay,
What I select for vegetation, that will not work. I mean, obviously, that's a major feature of this spectra, right? We can uniquely identify the elements by manipulating these bands. So band ratioing, it helps a lot. That's one of the spectral based algorithms we apply on the geospatial data.
okay, okay. Ma'am, can just elaborate how this geotiff data you extracted into the matrix format, because this data is complex in nature, I think.
Yeah, we it's basically set of some functions. Nowadays APIs are readily available which converts your data from one format to another. So what we, I mean, when we read the image, you read it in a matrix format. Okay, even see, it's a, this is a set of pixels. So if I require, I can even read it as a array, one element, I mean, one dimensional. I can consider it as a two dimension. Even if it's a hyperspectral data, I can consider it as a three dimension. So even it's a single image, I can manipulate by means of one dimensional, representing as one dimensional or two dimensional or three dimensional.
Is there any
It's
tool
my
to
requirement.
convert that one?
Sorry.
Is there any tool to that extract the data?
No tools. No, we can write this. I mean, it's, we can write the set of statements, right? We can write the state of statement that in what format I want to convert my, in what format I want to process my data, right? If I want to process in 1D format as a vector, I would be storing it in 1D format, right? That's just an array. So you read the image the way you are reading any normal image, and then you store it in the data structure. You use the data structure which is suitable for your algorithm. Now, for me, the data structure which, I mean, one which I have used is the matrix, because I was processing in terms of matrix. My threads are organized in a matrix, but threads, even I can organize as a one dimension, I can organize as two dimension, I can organize as a three dimension. So you always represent your data in that manner. Okay, if your algorithm is suitable for 3D, better you store your data in 3D format, right? So that's how we can arrange our data so that it would be suitable, and it will fit on the GPU architecture. That's the
Okay,
basis actually. Yeah.
okay.
There is
Thank
a
you, ma'am.
question from Anga Ahir, ma'am. Ma'am, please proceed.
Yeah, ma'am, I just want to know, can you give more focus on how we can use vector data for, I mean, GPUs, wherein we'll use vector data for query processing? Any specific framework or approach, something like
Post GIS, I had used it once. Okay. just to test whether really it's executed on the GPU or not. But yes, I mean, I cannot demonstrate it, but then I just tried executing one query, the typical one, like that the river crosses through which, passes through which cities. So then I tried executing that query on GPU, and then the same query which we usually write. So same query I had written, and then while displaying the result, it had shown that how it mapped on the GPU. So the GPU mapping was displayed once the query was executed on GPU. So that's how it. I mean, I didn't work much on the uh, this vector data, but yes, long back I tried executing these PostGIS queries on the GPU. But it's same query even without. I mean, you just write the same query. Only you need to that interface. We need to enable the GPU for that.
Okay, okay. Thank you, ma'am.
Yeah,
Thank you so much.
yeah. So probably somewhere preferences you would get the option to enable the GPU. Like even in MATLAB, it's you might be aware of, like MATLAB, we can enable the interface of GPU and clusters. So same way, PostGIS we can enable the GPU interface. Yes, there is one environment required for that. I just forgot. Mm, yeah, for PostGIS. Yes, but yeah, I mean, it comes with that. I mean, that once we set up for that configuration, it by default, it set up that environment. So we need not have to write, we need not have to change something in our code just to say that it should run on GPU. That doesn't require.
Okay, okay. Thank you, ma'am. Thank you so much.
There is one question in the chat window, ma'am. What parameters need to be considered when designing a deep learning model for computations on the edge devices?
What parameters need to be considered? Okay, because I myself have not worked, but I will try to answer. Competition on edge devices, because as we know that the limitations of edge devices is we cannot store a huge amount of data. That's limitation. Then yeah, there's a few others like uh, I mean something which would be or you may be considering the lightweight platforms at the edge side. Okay, and maybe lightweight operations as well. I mean, those devices are capable of, like Jetson, it's working. I mean, it does the task in parallel, but then still you cannot compare the Jetson and then NVIDIA A40. There is no comparison. It has a restriction on the computing power. Okay, so yeah, maybe uh, what you can avail to the end user, okay, without much overhead to the device, because a lot of physical damage chances are also there at the edge. So those are some of the things that can be considered. But yeah, I'll make it sure that I'm not quite well versed with this edge. I'm just aware of this thing. I have never used this kind of technologies for any computation, but this is my logical answer to the query.
Yeah, participants, anyone have any question? No. Okay.
Yeah.
Thank you very much, ma'am,
Yeah, or
for
even
enlightening us.
if any other
And
query, you can reach out to me later. I mean, if possible, I'll try to answer. Right. Yeah.
yeah, somebody raised hand here. Anyone want to ask any question? Okay. Thank you very much, ma'am, for enlightening us on the GPU, suitability of the GPU for the remote sensing, high performance computing, along with the case study on oil spill detection, as well as you have emphasized us on the band ratios of the GPU, multi-level parallelism for the massive data using the GPU. I hope most of the participants are from the same area. They got very much information from this informative talk. And I deeply appreciate on behalf of the RAIT and as a co-coordinator of this ATAL FDP, I deeply thank you for taking out your valuable time and giving your knowledgeable information to all the participants. Thank you very much, ma'am, for joining us.
Thank you. Thanks a lot, sir, for this opportunity, and thanks to the participant for listening me patiently. Thanks a lot.
Yes, thank you very much, ma'am. If any doubt is there, so we'll be in contact with you on the email itself. So we'll send you any queries there. Yeah,
Sure.
thank you very much, ma'am. We'll look
Thanks.
forward to you for the next upcoming ATAL FDPs as well as for the college STTPs.
Thanks.
Thank you very much, ma'am. So, dear participants, we have 5 minutes of break. So, we have with us our next speakers. So, Dr. Suryakant Sawant, sir. So, we'll take 5 minutes of break and we'll come back. Now it's 7:10, so 7:15, we'll start our next session. Hello everyone. Am I audible to you?
Yes, sir, you're audible. Am I audible?
Yes, sir.
Hi, this
Yeah,
is
yeah,
Suryakant
yeah,
from.
yeah, sir. Yeah, sir. Yeah, sir. Okay. Again, I welcome you all into the second session on Geo-AI innovations in AI for improved spatial data processing ATAL online 1 week FDP sponsored by ATAL AICT. I welcome to Dr. Suryakant Sawant sir. Dr. Suryakant Sawant sir currently leads in DFI Sky remote sensing research team and is responsible for researching and executing the various remote sensing use cases for the agriculture. He has filed 12 patents and published 35 plus research papers in international research forums like reputed journals and conferences. He has 12 years of experience in industry and academic, extensively used multispectral, hyperspectral, and synthetic radar based Earth observations for the agricultural applications. He has also worked on hyperspectral sensing for canopy, nutrient estimations, soil moisture estimation, crop variety identification, pesticide residual analysis, and disease identifications. He is a life member of the Indian Society of Remote Sensing, ISRS, and the Indian Society of Geomatics, ISG. He has conducted workshop sessions and on various applications of IoT and sensor web for weather and crop water management. His areas of research includes the remote sensing of vegetations, IoT and sensor web for agricultural water management, geographical information systems, hydrology, satellite image processing, and various AI applications in agriculture and forestry. I welcome you, sir, on behalf of RAIT in the second session, and I thank you for giving your valuable time and joining us. It's over to you, sir.
Yeah. Thank you for kind introduction. I will share my screen.
Yes, sir,
So,
you can share.
yeah, I hope I am audible. I'm trying to share my
Yes,
screen and let me know once the screen is visible.
yes, sir. Yes, sir.
So,
Your screen is
today,
visible now.
yeah, I hope my voice is also audible. There is no lag.
No lag, sir. You can continue.
Okay, thank you. Yeah. So, thank you for giving me this opportunity to present our work and my research topic, which is actually very close to my heart, which is application sector, that is agriculture. In my background, there was one thing that was missed, is like my background is interdisciplinary. I am not from computer science background. My BTech is from agriculture engineering. Most of you may not know whether this branch exists. It is called as agriculture engineering. And then I did my master's and PhD from IIT Bombay. And I extensively worked in this area of application of remote sensing, GIS, and IoT in agriculture for various applications like crop management, crop water management, vegetation monitoring, etc. So today, what I'll be sharing with you are some of our experiences and our approaches that we take while solving the problem in agriculture sector. And we call it as agro-geoinformatics and sky-earth convergence. So when we say sky-earth convergence, the sky is above ground, the earth is above the soil and below the soil, and the convergence of these two, the sky and earth, if we do, we can bring a lot of information onto the table. But before going to the sky and earth convergence, we can understand what is agro-geoinformatics. So agrogeoinformatics is not a single branch. It is a combination of multiple disciplines which are starting from multiple sciences, like starting from computer science, data sciences, geospatial sciences, environmental sciences, and there are also core branches of agriculture that are like agronomy, animal science, horticulture. These all involve together for solving the agriculture related aspects, and that comes under the agrogeoinformatics. Only agroinformatics is about telling the information about agriculture activities, etc. But when the word geo you bring into the this combination, the geography specific agriculture, because there is a lot of variation that happens in the agriculture sector, that is brought onto the table, and it depends upon the region and also the area where we look into. So for example, if you are looking into agriculture sector, which is southern part of India, it is completely different than that of a northern part of India, including the cultivation practices, the seasonality, the crops that are grown, the soil types, etc. There are multiple things that come in play. So agrogeoinformatics is nothing but the combination of all these branches or all these sciences together. And when we combine this, we can generate a very insightful outputs for end users. So end users can be multiple end users, including farmers and other stakeholders like companies which are selling fertilizers, companies which are producing hybrid seeds. There can be multiple such end users that can come in play. So my talk today will not be concentrating more on the basic computer science or data analysis side. I will be mainly concentrating towards the application side and how the practical application of this technology is being done using the computers and electronics and the advances in cloud computing platforms for agriculture application. So this picture will tell you multiple things. So this picture is actually about the sky and earth convergence. So sky can include the data set from the satellite or drone, and that data set can be multispectral, hyperspectral, synthetic aperture radar, or even LiDAR. LiDAR is like light imaging and ranging. So these multiple set of data sets that can be brought from the sky. There can be the earth level sensors like soil moisture sensor or typical weather station kind of sensors where it has rain gauge, it has anemometer like which tells us the wind speed, wind direction, etc. And the temperature and humidity sensors. So these are the sensors which can be above ground, that is above the canopy of the crop, and they can also be below ground. So below ground means inside the soil, and they will be able to measure multiple such parameters. And when we combine this information from earth level distributed sensors and the sky level analysis from satellite and drone based analysis, and when we fuse that together with the agri knowledge base, we can bring the insights onto the table. So these insights are in terms of early detection of certain pests and diseases, identifying the yield, looking into the how the crop growth pattern looks like. So here, if you see the view for potato crop, this is a typical view for potato crop where it starts from day of planting, the growth of crop starts, and there is a ground cover that increases to 100% coverage of the vegetation, and then similarly the blue line tells the satellite based observation, and the green line tells about the observation that is collected by the field staff by going onto the field and collecting the observation. And there are certain stages like emergence, full emergence, ground cover, 100% ground cover, then the senescence. The senescence is like after maturity, before harvest, there is a stage that starts for the crop, and then the harvest that happens. And this is the typical cycle of potato crop. And below graph shows that when there was a cloud cover in a given satellite image, because cloud cover is one of the major aspects that I will be talking about in my subsequent slides. When there is a cloud cover, how much was the percentage of cloud cover and how much was the observation that was occluded by the cloud. So this insight can be also seen this way. So the other way of looking into this information is looking as a pictorial representation of that field. So if you see, this is the field which is located in some American geography where you see the latitudes and longitudes. So this is the negative longitude. That means it is in the western hemisphere, and as latitudes are positive, it means it is in the northern part of above equator. So these kind of things, they come out of domain and the domain understanding that we get from the geospatial data analysis. So I will be talking about these things as a part of discussion also today, because I may not be covering entire 1.5 hours with my presentation. I will be hardly covering my presentation in 30 to 40 minutes. So here, when you see, the point here to tell is like sky and earth convergence is important thing for identifying the agriculture activities and knowing how the crop is growing onto the field and reducing the cost for customers. So here a customer can be a customer who is cultivating the potato, a farmer, or even a commercial grower of a potato, which can understand whether the farmer field is performing better and what is the stage, growth stage of the particular field, and when the harvest will happen, so that I can plan some harvest activities like procurement of that potato from the farmer or logistic planning, etc. So such things can be planned and such insights can be generated. So here, the basic insight or objective behind showing this screen is for agronomist or a person who is monitoring the fields of these farmers can understand easily what is this field going through. And this is like a potato field which has a different stages at different timestamp, and this tells a better view into certain regions which are good performing, certain regions which are bad performing or not so good, or they can be stressed regions. So this is actually a very simple view which is generated using the vegetation index. So in last presentation, ma'am was talking about vegetation indices, normalized difference vegetation index. So there are multiple such indices. I will also show you some of those index databases where how these indices are cataloged and their information is collected. So I will show at the end of my presentation. So the objective here is to show how the sky and earth convergence can be helpful and how we operate in TCS about the sky and earth convergence. So when we look into the sky earth convergence, the point, line, field and region. So the coverage depends upon the sensor we place. For example, in the sky earth convergence, there can be sky to earth convergence, there can be earth to sky, that is earth led convergence and sky led convergence. So now I am talking about earth led convergence of the data, where my objective is to understand how is the distribution of soil organic carbon. So when I am talking about all of my presentation, I will talk some terms about agriculture. The soil organic carbon is the important part. Brief background I can give about soil organic carbon is in Indian climatic scenarios, like we have the temperate tropical climate, not temperate, tropical climate where we are very close to tropics, the Tropic of Cancer and Tropic of Capricorn. So these tropics, they have very high heating because of solar radiation that we receive. And our soils are very poor in the soil organic carbon percentage. So when the global, if you see, the globally soil has a capacity to store a lot of carbon as a storage, and the soil organic carbon is the one of the medium which can store the carbon, the atmospheric carbon in terms of soil organic carbon into the lower layers of the soil. When I say lower layers of the soil, they are below 30 centimeter of the soil. And to do that, or to understand how is the variation of soil organic carbon in a given region or in a given field, what are the techniques that we can use and how we can make those techniques very cost effective, because I cannot go to every field and collect the soil sample and analyze that. That is a traditional way that people are doing this thing, but still that is required. But that at a scale, you cannot do that in very large areas. So to do that on large areas, people have come up with very novel ideas where we work with our partners. So here the data set that gets collected are the point data sets. That is field level soil sampling. So less number of soil samples can be collected. There can be tractor mounted gamma ray spectroscopes. So gamma ray spectroscopes are spectroscopes do collect data in the gamma region of electromagnetic wavelength. So yesterday there was one presentation from one of the professors from IIT Indore. He presented about basics about remote sensing. I hope you all remember that. What is raster data, what is vector data, what is electromagnetic spectrum and all that. So today I will not cover that. I will directly go to the spectrum and its applications. So here this gamma ray spectroscope will collect the observation in line format. So when I collect the data, my one observation will be in the line format. And if I mount that line instrument on the tractor, it will become like my line scanner. And I can scan the entire field as a polygon. So, and if I mount this line scanner on drone, I can cover the field, but I will be able to cover very small region of the field. I will not be able to cover very large region because of certain constraints of the drone, energy and the energy consumed by the sensor, the payload size of the sensor and all that. And the other part is I can have the satellite data, which can be also multispectral synthetic aperture radar observations and other satellite data sets. So how this sky-earth convergence is helping here to understand or to solve this problem of soil organic carbon estimation or effective soil organic carbon estimation with low cost is we are using two type of data sets. One is field level sampling and another one is tractor mounted gamma ray spectroscope. So gamma ray spectroscope has covered very small portion. Here this 25-acre patch in this field you can see is covered by this tractor mounted equipment. And there are a few samples that we randomly chose, around 3 to 4 or 5 samples that are collected by the field level soil sampling. Just again, I will reiterate, this small portion of the field is around 25 acres. The entire field is around 80 to 180 hectares. So this is like Canadian geography that we are looking at. And when we use the sky-earth convergence, the multispectral data from satellite can be used in conjunction with this data set, and together we can build a model which can be a machine learning model or deep learning model. The model choice can depend upon the complexity that we intend to have, and based on that we can estimate for entire region what is the soil organic carbon distribution. And if you see these ranges in India, typically from basic understanding you can understand there is nowhere in India the soil organic carbon that we can see more than 1.5 or 2%. In forest, some areas in very deep dense forest in India, you can find the soil organic carbon more than 2 or around 2%. But this is Canadian geography. It is temperate region where there is very less sunshine and very short duration. There is oxidation of the soil organic carbon that happens. That's why these areas, this soil organic carbon is preserved, and that's why they are saying that they are most carbon neutral or they are most carbon efficient country in the world. But they are still, their carbon emissions are increasing because of application of nitrogen fertilizers and degradation of this soil organic carbon in the layers of the soil. Again, coming back to our problem, this soil organic carbon estimation. So here our model, which is built based on multispectral and synthetic aperture radar satellite data and the tractor mounted gamma ray spectrometer observations, we are able to scale our observation to a larger region. So if you see, this is around a patch of 5,000 to 10,000 hectares, which is on the right side shows the estimated soil organic carbon. And the left side, it shows small patches that are collected by using the gamma ray spectroscope. So similar way, if there is a data set which is very pinpointedly available, which is geotagged and the time dependent, because see, whenever there is agricultural system, there is a coverage of soil that happens during the season. When there is no crop, the soil remains bare. There is a certain amount of residue of the crop that remains on the field. But here in this case, the timeline is important in two perspectives, because there is the snow cover that also happens in the region. The certain duration in the time in a year, the entire region is covered with snow. Other part is we also need to know when the samples were collected, when the observations were made, and when the cloud-free satellite data is available, when the ground is also clear. So then only this kind of observations can be used to build our model, and to model performs better on those kind of observations. So this is the one insight based on the Earth-led convergence, where we call it as a sky-Earth convergence led by Earth. But another convergence can happen, where sky can lead the Earth force or the ground force. So here the satellite data, this is typical tea garden in Assam. This is the use case from Assam where tea garden is demarcated by the fields. These are large gardens where management can be much more efficient. The satellite-based insight shows us some hotspot in terms of vegetation index, and this hotspot needs to be looked in a bit detailed way. So what can happen is there can be a UAV or a drone-based observation that can be used, and then again our YOLO kind of models where we can either have on edge or on computing device the analysis of this data and understand which are the hotspots in this geography and how field force, the persons who are collecting the samples, can reach on the ground and collect the data. So this is actually happening through sky and earth convergence, where sky is leading the earth to take some actions and to understand in a better way the stressed conditions in the given geography. So here there are two pests and diseases that you can see, red spider mites and those leaves that are infested because of red spider mite. The other sky and earth convergence is a fusion of data from sky and earth and having the process-based models. So process-based models are nothing but the physics-enabled models you might be hearing these days, like AI is entering into process-based modeling scenarios where physics-based models are being fine-tuned by AI. And for that, you need understanding of process-based model first. So process-based model means, here very simple example I am taking. You consider soil as a storage and this as a tea bush, where on the top there is a harvesting portion that is like the top one leaf and a bud, or the portion that gets harvested. We call it as a top or tabletop of that particular tea bush. And there is a root system. So tea garden, those who are knowing, for them it may not be the new information, but the tea gardens, when they are planted, they remain in the region for more than 70 to 80 years. In India, there are still tea gardens, they are 100 and more than 100-year old. So these tea gardens, they have very good root system, they have very good channels and arrangement in the field. But the problem is that they don't have irrigation system, because these are very huge areas and irrigating those areas is very difficult. So the objective here is to understand when to schedule subsistence irrigation in summer season, and when understand when these tea bushes are undergoing this stress. So when we consider here the soil profile is this profile where there are certain input parameters and there are output parameters. So input parameters are in terms of the rainfall or irrigation that comes as an input to this profile, and the output is like deep percolation. We cannot do anything to deep percolation. The water that can easily flow because of deep percolation, it can go away from that particular field, and the runoff that happens to channel into the river or the small streams that are nearby. And the other part of output is in terms of evapotranspiration. So this is the process-based scenario where the inputs from satellite-based indicators like vegetation indices or soil-based soil moisture can tell us to scale or understand over the larger region what is the scenario. And then the earth level sensors like weather station, there can be one local weather station for entire garden. So that weather station can tell us how is the temperature, humidity, wind speed, wind direction, solar radiation parameters. And then we model all these components, evapotranspiration, and understand rain and irrigation. And then on daily basis, we can understand how much is the consumption of the water by this crop, and how much is the deficit, that is irrigation demand of this crop, and when the crop is undergoing the stress. So this temporal pattern is modeled using the process-based model, and the insights are provided by the sky and earth component to scale it up in a better way and to fine-tune that model to a particular regional condition. So if I don't have the sky or earth component, what will happen is my model will be only a theoretical model. It can work on dummy data or maybe a theoretical data set. It will work, the model will work. Because it is physics-based model, it will also generate the output. But the problem will be that it will not be specific to the tea garden, which I am looking for. And it will also not be specific to the conditions that are happening at that particular season or time period in the season. So these inputs, they help in fine-tuning my model for particular region, particular season, and also for time duration. that is on the daily basis, and understand what is the irrigation requirement for the given crop. So similarly, with this, I can take some pause, and if there are any questions, I can take. Otherwise, I can move into the next aspect of the cloud cover and cloud removal. Any questions or any comments until now?
Sir, how much is the cost involved to measure this data from as considered as a 1 hectare or 1 acre?
Yeah, see, typically when we look into the soil organic carbon estimation in US geography, the cost is around right now $10 to $15 per hectare is the cost. And with the sky earth convergence, we can bring down it to less than $1 to $2. So that is the cost proposition that we bring in. So this, if you are looking at specific use case, I will talk about multiple use cases in a later phase of my slides. There can be multiple such use cases. It depends upon the complexity of that use case and the area that you are observing. So when you look into the satellite data, there are two types of satellite data sets. There are open source satellite data, which is very free of cost, but you need cost for computing and generating the insight on that satellite data. So that computing cost is going to bring some cost onto the table. So typically the cost proposition depends upon the area that you are looking into and the complexity of the use case that you are looking into. So I cannot directly answer that question, how much cost it goes into. But
okay. Because free data is not available for specific reason, no? Right?
No, free data is globally available. It is not that. Satellite data, which is from open source community, which is European Space Agency, the NASA, and some of the ISRO data sets are also free and open source. So these data sets are globally available. They are not like restricted to any geography or any region. Only thing is that having just open source data or free data is not sufficient. You also need ground truth. Ground truth means the physical presence on the ground where you have something for validation, and that helps you to validate the insight that you have generated. Then only your model becomes validated and usable in that region for operational use.
Yes, because the real-time data is very important.
Yeah, this data set comes real time. I will show you some things here now. Okay, if there is any other questions, are there any other questions other than this data part? I will address your question. Any other questions from anyone? If there is no, we can proceed with the next part.
Yes, sir, proceed with the next.
Okay, thank you. So this is the example of a cloud removal. So when there is a monsoon season, as one of the question that came just now, the data is not available continuously or data is missing. The one issue of this data set, the open source data set that is available, there is also cloud cover, because this data set is a multispectral satellite data and it has a cloud cover issue. You may say that, yeah, I can use basically machine learning algorithm and I can remove this cloud and then I can use it. But when you use machine learning algorithm and remove the cloud, you will get only this much patch, the central patch that you see, that is cloud free part. Other entire black region is the cloudy region, where you cannot generate any insight because this is a geography specific data set. But there are other approaches, the fusing of multiple satellite data sources. Like Sentinel-2 has a frequency of 5 days because of there are two satellites. Sentinel-2 has Sentinel-2 and Sentinel-2A. Those who are very new to these names of satellites, I will just pronounce them properly. Sentinel-2 is from European Space Agency. There are two satellites which are in multispectral region. The program is called as Copernicus program, where multispectral satellites are launched in the polar orbit, where there are also synthetic aperture radar satellites. Their name is Sentinel-1, and there are air monitoring satellites. Their name is Sentinel-3, and Sentinel-5P are the other satellites that are launched under Copernicus program. There is a MODIS satellite that has been launched by NASA, which is, there are again two satellites. Their name is Terra and Aqua. So Terra means terrain and Aqua means the water. So these two satellites, they have a different frequency. The Landsat has a series. So Landsat started from 1980s. So if you go back in 1980s, there were Landsat 4, Landsat 5. Then Landsat 6 was not able to launch because the launch vehicle itself failed and the satellite was damaged during the launch, and entire satellite burnt out in the orbit. But Landsat 7, Landsat 8 and Landsat 9, these are operational satellites. Out of that, Landsat 8 and 9 is operational now. Landsat 8 is operational from 2015 and Landsat 9 is operational from 2 years back, that is around 2022. So these satellites, they have different frequencies. So point here in telling this is, this view on the right side, the NDVI output that we have generated, we have used our algorithm to combine or fuse this data set from multiple satellites. So can I generate an output after every 10 days using these multiple satellites? Because MODIS has a daily frequency. Landsat has a 8-day frequency. Sentinel-2 has a 5-day frequency. I can fuse this data together and remove the cloud and generate the insight for agriculture portion. So this portion, that patches that you are looking at, the urban and the water portion, they are removed, and only agriculture portion areas are covered. So this is the armored mandal or urban sub-district from Nizamabad, Telangana state, which is the insight that is generated for that particular region. So the vegetation index is here, NDVI is the output that is generated. So this way, the models can come into the play. They can help you in generating the output and augment your data and generate the output for your region. And this is one of the example that we use. So similarly, if we want to monitor the seasonal progress of agriculture in entire India, what we have done is every 10 days we applied the same algorithm, the algorithm that I talked about in this view. The same algorithm we applied and we generated the insight for entire India. So typically at 10-meter spatial resolution and 32-bit pixel size, the size of entire India comes around 10 GB. One layer comes around 10 GB. So what we do is we use parallel computing, as ma'am was mentioning in the last presentation, the high performance computing. We used cloud-based high performance computing parallel processing operations, and multiple districts and sub-districts we processed in a kind of a serialization. So that serialization helped us in getting the scale and generating the insight within 2 days. So these insights are generated within 2 days of satellite data acquisition. I'm not telling historical view. So this historical view right now you are looking into is just to represent or just to show as a screenshot. But when you look into operational use, suppose today is cutoff date. So today is 3rd of December. I can generate the output for 20th November to 30th November by 3rd of December. Like within 3 days of acquisition of satellite data by multiple satellites, I can fuse them and generate the output for entire India. So that is the capability that we have built. And we are not only processing it for 1 year, we are processing it for multiple 3 to 4 years, and comparative assessment we are doing. Like last year, what was the condition, and this year, what is the condition, so that we can understand how is the anomaly of that particular vegetation index and how the vegetation is progressing over the region. So that insight can be in a better way. So because this is a pixelated view on very high resolution pixel resolution, that is 10-meter pixel resolution. Even I'm calling it very high is not good terminology for that. It is still moderate resolution. Very high means the sub-meter resolution, like the Google Maps that you see, the meter and sub-meter resolution. So this is 10-meter spatial resolution satellite data. So when you look into entire season for vegetation index, you can easily observe that. See, this is the typical Rabi season. Rabi season means starting from October till April. So where our crops like chickpea, in some regions there is rice grown in this Rabi season, and in some regions the wheat and other crops that are grown. So you can see the progression, like how the green progression that is happening across the season and how the harvest progression is happening. Like you see central India in February and March, it is green, where there is a very good cultivation of wheat that is happening across Uttar Pradesh, Bihar, Punjab, Haryana and central Madhya Pradesh. And Rajasthan still in entire duration, you see that desert region always remains darker or in the red color. That means there is no or very less or sparse vegetation that is growing. But the major crop, this map is actually the representation of sub-district level entire country and for that particular season. So Maharashtra, if you see central Maharashtra, it is dry at certain point in time. in February, after February, the central patch of Maharashtra and Karnataka becomes dry, and in later phase again it gets drier, and because the vegetation gets harvested. By March and April, the most of country gets the crop gets harvested, and then again you see some part of Kerala start getting greener, because Kerala and some part of Tamil Nadu and West Bengal, they are such regions that they always plant rice because they have plenty of water and they plant rice, and there they have multiple cropping systems. Like Tamil Nadu on its own has 8 to 9 seasons of rice, but they are parallelly occurring seasons. They are not demarcated like our typical Kharif, Rabi, and summer season or Zaid season. But this view actually tells you multiple aspects of entire region, and this helps to customers to plan their logistic. So logistic in terms of putting pesticide in particular markets, which are the regions to target, which are the regions which are better this year, which were not good last year. Like that, this understanding can be generated very easily using this kind of analysis. The other part is combination of soil moisture. So if you see the soil moisture, the variation of soil moisture is like as post-monsoon season starts, the residual soil moisture in the soil is used by the crop. Okay. When I say residual soil moisture is like the soil moisture that is left after the rainfall or any season is used by the crop. And if there is any cyclone or something that happens, then only the soil receives the moisture. Otherwise, whatever left after the monsoon season is being used by the crops, and till the March comes, the soil get very drier and drier. So their soil moisture percentage reduces to less than 5%. So if you see here the March map of 2022, entire region of India has, or peninsular region of India has got dry because of lack of soil moisture. And at this point in time, there is no crop that is growing, in only few patches where there is irrigated areas, because this is aggregated view. You will again get misguided from this view. This is aggregated view on the sub-district level. It is not like view of a one farm or one field. This is aggregated view of that region, and the regional level insight is generated using these maps. So when you combine the seasonal vegetation health and the soil moisture, you can definitely generate the insights to understand which are the regions which will face water scarcity during the season, and those regions that will need subsistence irrigation, that is survival irrigation in a given season, in mid of January or in mid of December. So such identifications can be very well done by using such kind of data analysis techniques and the insights that are generated using the satellite data. Coming into the overall opportunities in agrogeoinformatics sector, these are the crop planning till the post-harvest use cases that are being targeted. So starting from soil moisture estimation for crop planning or crop suitability or crop planting suitability, till the harvest, how much is the harvest and what is the tillage that has been done in the field. These are the use cases or the spectrum of use cases that can be covered, and certain level of use cases that are not possible using satellite data or only satellite data. These are like weed detection, the crop damage assessment, very specific field level crop damage assessment is not possible only using the satellite data. It always needs ground truth and the ground level observation. Soil nutrient monitoring, as I was showing one of the examples of soil organic carbon estimation there we cannot directly use this satellite data. So these data sets which are derived or available from satellite, they have their own limitations. They can be used up to certain vegetation levels or a certain level of the pixel resolution. So then there are certain challenges. So challenges are there in terms of technology and infrastructure. One of the challenges that ma'am explained in the last presentation is about the data volume, the cost of data, the cost of processing of data, and the velocity of data. So high performance computing is coming in that space, and it is helping to generate insights or better insights using the satellite data. Then interoperability. Interoperability is a major challenge where there are different data types and there are different formats that are coming, and those are creating a challenge in understanding and creating plug and play environment for IoT sensors or even for satellite data analysis. Then the operational use of certain data sets. The field size is a major limitation in India. But in some of the other regions, the other parts are like intercropping or mixed cropping. Like in central part of Maharashtra, if you see, the cotton is planted with red gram, and sometimes in some regions, the red gram and soybean are also together. So this kind of scenarios, it is very difficult with the satellite data to detect which is the exact crop in the field. So such limitations, a user or a person who is handling such data sets should always understand the limitations of those data sets and then approach the problem for a given geography or for a given region. I hope I am audible. My microphone has some issues. Can somebody?
Yes,
Yes, you are audible.
yes, you are audible.
Okay. Yeah, thank you. So coming to the other issues, public policy related issues, till today, like there is in India, there are certain challenges or certain issues with the using of data set, which is a very high resolution satellite data. That is, if you want to use sub-meter satellite resolution, like less than meter resolution, you need to take approvals from the ministry, that is NRC, that is National Remote Sensing Service Centers, and other agencies, so that you can use that data set. But the data set above 3 meter spatial resolution, you can easily use it. That is the policy decision that depends upon region to region. Like Brazil has other policy decisions. The US has certain other policy decisions like that. These policy implications also play a critical role in using this geospatial data for agriculture applications or in this agro-geoinformatics space. And another part is e-waste and the personally identifiable information. This is also one of the challenge. So today you will say that can I not monitor every farmer whom I am procuring the potatoes from? Like suppose you are a potato aggregator or potato seller or potato processing company, and you want to monitor all the farmers, how they are producing the potato, what is the quality of potato that they are generating. There's the issue of personally identifiable information that may also arise, and in certain regions, those compliances and those understanding we need to always have. Then electromagnetic interference. So this electromagnetic interference is a major challenge in synthetic aperture radar. In Indian geography and certain regions, because of other radio antennas and radio infrastructure which was traditionally available, for satellite data acquisition, the electromagnetic interference creates a very noisy kind of picture, and that damages the analysis or possible analysis in those regions. So those regions can be easily identified, but that is still a challenge that remains from the environmental and ethical perspective. And there are intellectual property related issues that may come in play during actual use of satellite data and algorithms. When we look into the business considerations, see, we are not the team of only domain experts. There are also technical people that we need. We need business people and market understanding. So whenever we go into a business considerations, we understand the business idea, the problem that is at hand, then who is the target audience, whether the farmer is my target audience or I am working in the B2B space where business is my audience. And based on that, we create value proposition for them and we identify technology stack. Like in last presentation, ma'am was saying PostGIS and PostGRE SQL that can help in doing certain analysis. But that is one of the technology stack which is open source. There can be commercial technology stack which is built by ISRI, which is you might be knowing from some of the advertisements or any GIS kind of lectures, where ISRI is a company which generates the insights based on the geospatial data set. And there are also some other companies like Mapbox and other companies are there. And these are tools. So open source tools, they can be integrated together and you can generate a novel solution for a given industry. Then what is the market potential? That the second phase that comes into play is like, what is the market potential for my business model and how my overall landscape will look for 3 to 5 years. And then where do I venture and which are the markets where I can venture? Like whether should I venture in the LATAM, that is Latin America, that Brazil and other region, or should I operate in the European region and Americas or Northern Americas? it depends upon very strategic understanding of the business portfolio and the region. And then the technical feasibility, deployment, and all that comes as a technical challenges and the team experience. So here, team experience, we have a team of interdisciplinary team where there are technology people, there are computer science people, there are electronics people who can understand their domain and they can relate this domain with agriculture, and they can help in solving the challenges which are at hand. Then the investment, as we are in the research, we still need investment from our verticals. We don't get flexibility to operate in any region or any topic. So that investment is also planned in a given strategic way. And the regions that are identified for the sale of product that is generated. And of course, the regulations and compliances that are also being met for that given geography. The second part here is B2B space. When you look into B2B space of this agro-geoinformatics solutions or customers, they can be agri supply chain, where farm to fork kind of mechanism is there, where companies those aggregate the produce from farmers and provide it to the customers. Right now, there are many such companies like, Big Basket and all other companies which are operating in your neighborhood. The other part is banking and finance. So agri credit, agri lending, and agri insurance. This is major sector where we also look into, which was typically traditionally the finance business. But now there is, because of climate change, very a niche requirement is coming from this sector to understand what is the risk of the money that they are putting in this sector, agriculture sector. And how do they understand in a early stage the risk for their investments? So this is actually a sector where we are coming in play, and the agri input, post harvest, and the government departments. So government departments, they are typically Department of Agriculture, Water Resource Department, and administrative departments like Gram Panchayat, etc. But these are based on still traditional ventures in India. But in other countries, they are very strategically placed departments, and they operate multiple things even in private space. So they keep open source data. Like for example, in European Union, any data set that is available, which is satellite data or any data set which is non-personally identifiable, can be easily available for sharing. And that is the role that their local governments are playing and bringing on a very huge amount of data set onto the table for public use. And that is the part which is played by the local governments in those geographies. And their insights are also required by these businesses like banking and other sectors, because they will rely on these sources, like what is the area of that particular land, who is the owner, how it was the leasing done in the last few years, like that. So that kind of business that operates in this kind of space. Coming to the startups in agro-geoinformatics sector, I try to arrange those in different subsector wise, like the companies that are specifically looking into satellite data analysis services. So these, some of the names you might be knowing from India, like Cropin, Satshore, Amnex, Wasar Labs. These are like, some of them, they have evolved beyond startups. And most of these names may not be right now not feasible as startup. They might have evolved as a company, full-fledged companies. But they operate in this space, agro-geoinformatics space. But some of them are very niche. Very niche means I have mentioned here the SpaceX also. So because the SpaceX has a launching capability, now very small company like Cropin or anyone who wants to launch their satellite, they can just build the satellite from some partner and provide it to SpaceX. SpaceX will launch their satellite. Like that same way that is happening with GHG sat. Yeah, my microphone is dead. So am I audible now? Or is there any issue with?
Yes, sir, you are audible. Yes, sir. Yes.
Okay. So here what we are looking into is a view into the companies who are operating into different spaces across the spectrum of these technologies. Starting from services sector I was talking about. Then the drone-based services. There are certain companies, they are from India and mainly from US and other countries, where they are creating very frugal drone platforms where data can be easily covered over the larger regions, and that can be used for agriculture applications. Of course, their solutions are not limited to agriculture. Their solutions are also spanning across multiple areas like mining, forestry, environmental aspects, etc., and disaster recovery and disaster management. But here I'm mainly talking about agriculture and their applications. So very niche. Again, another company which was acquired by John Deere, which is Blue River Technology. They have created see and spray application, the tractor mounted equipment where the weeds will be detected at very real time situation, and the spraying will happen at this on the spot. If there is no weed, no spraying. So that way, the technology was acquired by John Deere, and now John Deere has offering, or in Northern Americas, John Deere has such kind of sprayers now operational in the field. And as I was talking about the satellite launching services and satellite launching companies, the Pixel is a startup from India who has launched the first hyperspectral satellite, which is commercial hyperspectral satellite in space. And their satellite is not operational yet, but it has been launched in last year, and now they have planned for launching few more satellites. So they used SpaceX and Indian Space Research Organization's capability to launch their satellites. So the Antariksh Corporation from India is the commercial wing of the space research, where they launch the satellite. So Antariksh Corporation, if you see here, is like launching service for those private satellites. And the GHG Sat is the company who has committed their satellites for methane monitoring. So methane monitoring is a major issue in agriculture sector, where livestock is a major producer of methane, and methane emissions are very critical and very potential climate risk or climate hazard, 4 times potent than that of a carbon dioxide. So although the nitrous oxide is also more potent than the methane, again, that is another thing that you can learn from literature. But I'm just giving an overview about these technologies and the companies they are operating across the spectrum. Coming into the data sources. So just for your information, those who want to know what are the data sources that are available, these are the satellite data sources that are available. Maxar, Airbus, Planet, these are commercial. Landsat, Modi, Sentinel, these are open source. Anywhere from globe, you can access this data for any region of the globe. Weather data sets. So there are multiple weather data providers. Some of them they are free, some of them they are commercial. So NASA Power API is free, but others are like commercial data providers with a minimal cost. They can also provide you the data. Geospatial boundaries. Whenever a researcher starts any problem, the issue comes like, where do I find the geospatial boundary? So Diva GIS, Bhuvan, and local government websites will provide you these geospatial boundaries for your research or for your analysis. Soil data. Soil grids is one of the good data set which provides you the soil data set. Then the digital elevation model. So digital elevation model is nothing but the terrain properties. Suppose you want to create a case study on the flood analysis. You need topography data for that region. So SRTM, CartoDEM, Aster, and Tandem X. These are the digital elevation model data sets that are available. So like that, I will not count all the names, but these are all different tools and data sets that are available. If you are looking for specifically cloud-based offerings, you can, of course, go and look into Google Earth Engine and also Microsoft Planetary Computer, that is data store, and ML. If you are already having some credits on AWS, you can look for AWS Registry of Open Data. There you can get all these data sets open source, and some of the commercial vendor data sets easily available on the machine learning platform for using it for your applications. And there is routing service and route data sets. Like suppose there is a certain use case you want to have from rural to urban areas and understand how is the routing mechanism working. So for that, there are certain routing APIs or routing mapping services are there that you can use it in your models or in your platform. So this was in short about our research area, the work we do. And with this, I would like to take a view into some of the questions. And after going into that, I would like to provide some view into some open source website that will tell you certain insights. So right now we can open it for questions, and then we can go into some insights.
Thank you very much, sir. Participants, you can directly ask the questions to sir if you have any.
Good evening, sir. I am Shailaja. I want to know know about how to extract potato information from the satellite, sir?
Yeah. So see, the potato information, when you say you have to be specific about your problem in terms of two ways. One is whether you want it on the field level, then you need to have a field boundary. If you want on the regional level, for example, in a given sub district, how much is the area is under potato? If that kind of problem is there, then you have to go for the classification problem. So in that classification problem, you will do crop classification. Typical crop classification problem will have multiple classes like water, urban, forest, agriculture. And in agriculture, you will have subcrop like potato versus no potato. So these classes, if you use the classifier or build the classifier using this kind of data set, then you will be able to identify in a given region what is the area where potato is being cultivated and which is the area where potato is not cultivated. This is the simplest example I can give right now for potato. But if you want
Okay.
to monitor for a given field, suppose you already have a field and you want to monitor the progression of that crop for that field, then you can have a boundary and use certain tools that I will be showing after this question and answer or during this question and answer. You can use this Google Earth Engine or some data extraction tools and extract the data in multiple time series and use that for your model generation for given geography.
Okay. Thank you, sir.
Yeah, good evening, sir. My question is, can you give some more research-oriented problem statement in this area?
Okay, research-oriented problem statement.
Yeah.
So, are you looking into specifically any domain specific
Yeah,
to
because
agriculture?
I am related to the computer science engineering department. So, how it will be useful, because I don't have an idea of agriculture domain and all. I have a domain knowledge of computer engineering. So, I can, in this regard, how you can give me some problem statement which I can select or give to our student for doing some research work.
Okay. Uh, See, one problem which I can tell in terms of these are multiple use cases. So when I say use cases, they can be also problems for research, and it depends upon the time duration that you are looking at. So one of the internship problem that we had, I will just give you a view. There is a commercial hybrid seed cultivation that is happening in India across multiple regions. So when there is a commercial hybrid seed cultivation that is happening, the challenge is that whether there is a isolation of that hybrid that is properly happening or not. So this is the issue of space, time, and mechanical separation. So when there is one field which is hybrid seed A and another field which is hybrid seed B, and if it is cultivating maize, that is corn crop, the corn has a minimum distance requirement of around 200 meters to 300 meters for isolation. If that distance is not met, and in between that, if there is any other hybrid or any other variety of corn is planted, then there is isolation breach. And what will happen is there is a cross pollination that will happen, and that cross pollination will create issues in the progeny that is you are getting for the seed cultivation, and it is not good for seed business. So the problem that we gave for that intern was, of course, that intern was from again a mixed background, interdisciplinary background from agriculture and learning computer science. So there, to understand for a given polygon whether within the vicinity of that polygon there is other crop or other same crop that is growing or not. And if that crop is growing temporally during the crop growing phase, suppose the crop is 90 days crop, that is my flowering stage. And during this flowering stage, is there any field nearby that vicinity or within that circle of that crop whether there is same crop and same stage? That means it is in also in flowering stage. That means the major problem is space and time. So when I say spatial separation is that whether the field is within that range, that is space, and the time is that whether it is flowering at the same time. If it is flowering at other time, then it is not a issue for that particular field. So that student used the Python based programming, and the GIS data was the basic data. So GIS data is in terms of field boundaries, and then that student used satellite data to understand first what is the crop layer. The crop layer means where there is a corn, where there is no corn, like that. as previous ma'am was asking about potato, that student created first the map, the corn versus no corn map, and then for that field that he had or she had, uh, he used or the data set from weather sources, and that weather data set was in terms of wind speed, wind direction, and the accumulation of energy in that particular field, and that helped in understanding whether the isolation of space and isolation of time is met or not. So finally the insight will be in terms of whether this hybrid seed plot is well isolated or it is not well isolated. There is an issue with isolation of this hybrid seed. So this is one of the examples. Like that, you can think of multiple examples. I can keep on telling examples about maybe about pollution monitoring. Like even a given region, if you want to monitor the pollution levels, what is the pollution level in a given geography or given region, you can monitor using soil samples and machine learning algorithms. You can deploy and create special maps. And that maps can help you in understanding which are the regions that are having higher toxic materials or higher toxic chemicals. So that kind of problems you can easily identify. I hope I answered your question partially.
Yes, sir. Yes, sir. Thank you.
Good evening, sir. Myself, Bharti. Hello, sir.
Hi.
Am I audible?
Yes, you are audible, Bharti.
Yeah. Sir, you have shown the NDVI of India for each month. Sir, is the data available freely for everyone?
See, that was processed output for our one of the customer engagement. That data set we are not directly openly making it available. Output of that model. So the output that I was showing was the model output, but the raw data that we used for analyzing that data or analyzing or creating that layer is available open source. You can access that data and create your own layer. There is no issue with that. So, but the insight that is generated is right now not available in open source domain.
Okay. Sir, what is the frequency you are shown with respect to each month 2 times? So like that, can we get it for each day?
See, there are certain satellites or certain satellite data providers, those can provide you data on daily level also. Like there are commercial satellite data providers. The resolution changes. Suppose you want daily data, then open source data of 250 meter resolution you can get on a daily level. But 250 meter resolution means on ground 2.5 hectare, approximately 2.5 hectares as a 1 pixel.
So,
okay, 1 pixel of 2.5 hectares. That means you need to have homogeneous crop like sugarcane or grape or some crop which is homogeneous across that 2.5 hectares. But if you want to go sub-meter resolution, then you have to go for commercial satellite data providers like PlanetScope. PlanetScope has a daily coverage. They have around 160 or 200 satellites which cover the globe daily, and they can provide the satellite data on the daily basis.
Suppose if you want for only some small field, one field of less than half hectare, something like that. So which source you can?
Right now, no such daily level satellite data available. The best frequency that you can get right now is 10 days in Indian geography. And in European geography, the best frequency that you can get is 5 days. But of course, you can use fusion of the satellite data. Multiple satellite data sets are available. They are having multiple resolutions, and exactly there the research problem become. The fusing multiple data sets, the fusion algorithms are still limited, and like LLMs, the foundation models for using the satellite data sets are still in progress. There are no very high-end foundation models available right now in geospatial domain. One of them that is released by Prithvi model, which is by IBM, is right now available in certain use or for certain use, but still there is no operational foundational model for geospatial domain.
Okay, sir. So it is like basically we can take the raw data and we are expected to find the NDVI on our own, right, sir?
Yeah, right now that is the condition. There are certain companies who are providing solutions on the limited space. Like there is OneSoil. OneSoil is a company where you can download the application and you can demarcate your field and get the NDVI data for whatever duration that is available from their portal. So like that, there are some other companies, and there is also a platform called Google Earth Engine. So I was about to go to that. You can learn about this Google Earth Engine. It is open source. And after learning, you will understand how to use multiple data sets for multiple purposes. I'm sharing my screen. I hope my screen is visible.
Yes, sir. Visible, sir.
Yeah. And if any student is starting, like suppose there is a computer science student we take for internship, we train them in this basic 2-3 tools. One is like QGIS tutorials, then the Google Earth Engine, and then the person gets understanding about certain things, and then we show them these indices. Like ma'am was saying, there is a specific index database or indices that are available. So this kind of index database that helps you in understanding. There are multiple researchers who has worked across multiple years, and there are more than hundreds of indicators that are generated only for one satellite data. So these 249 indicators that you see or indices that you see, they are only for one satellite, that is Sentinel-2 satellite. So there is this data set or database that is there, which tells you satellite wise, indices wise separation and their application, and all that data is gathered together, and you can use it for any other satellite. So suppose right now I have selected Sentinel-2, I can select Landsat and understand what are the indices that I can generate using Landsat data for my application. And that application can be any application. As I was saying, Landsat 8 is operational. So see, these are the indicators that are generated or possible from Landsat 8 sensor or satellite. And these indicators will help in understanding multiple conditions about aerosol, vegetation, forest, soil, water, and multiple things. So they are not limited only to vegetation. Some indicators, they are also in thermal region, thermal infrared. So some of them, they are in shortwave infrared. So this shortwave infrared, they will tell information about water also. In some aspects, temperature indicators will be accessible using thermal band, and that will be useful in terms of water identification. Which are the regions where water is present and where the water is not present, or canopy water is not present. And another tool that is available, if you see, this is right now I am showing is Earth Null School, which is open project, which was created by a hobby enthusiast person, and the entire data set is open source used here. If for your information, this is the projection, which is like a cylindrical projection onto the flat map. But when I go for orthographic projection, it becomes a sphere. And when I enable kind of a scenario of a given region, I can track across the globe what is right now ongoing. Like few days back in month of November, we were hit by, or southern part of India was hit by cyclone. So how this cyclone got formed and how the excess rainfall that poured across certain regions, you can easily see using this portal. And this portal is nothing but the data set that is gathered from NOAA and other agencies. So if you go into the about portion of this portal, all the sources of data, they are given here with licensing detail and the tools that are used and all that. So you are free to use this and understand the data. These are the data sets that they have used, their 3-hour precipitation accumulation and all that data sets. So this is kind of exploration that people need to do during their research and research formulation, and understand those from the perspective of their research idea or research objective, and then use it for solving the commercial problems or solving the societal problems where the impact can be created for a community. So this is my submission for today. Any further comments, I can take it up. Thank you.
Thank you so much, sir.
Anyone have any question?
Surya sir, your presentation was very excellent. Thank you very much for your input, sir. And I have two doubts from my side. One, you talked about potato separation problem. Can you please say a crude methodology? How could we do that?
Okay. In this potato cultivation, see what has happened is the
Sir, you are not audible.
Sir, you are not audible. Suryakanth sir.
Hello? Yeah.
Prakash sir, could you call him?
Yeah, I'm calling him. Yeah.
Hi, sorry, there was issue again with my network. Am I audible now?
Yes. Now audible, yes, sir. Continue.
Yeah. Since like how many minutes I was not audible?
Last
Sir,
2
you're,
minutes, sir. Yeah, last 2 minutes.
sir, you're not
Okay.
audible right from the beginning itself, sir.
Beginning of this answer. Beginning of this
Okay,
question.
beginning of this answer. Okay.
Yeah.
So see, in this potato field, the requirement from customer was to understand how they can reduce the number of field visits and monitor at a large scale the potato plantations or planting of potato across the region for compliance perspective. When we say compliance is like compliance for the sustainable cropping practices, because sustainable cropping practices are nothing but like whether they have planted the crop in a given duration and whether they have planted after the potato certain cover crop. Cover crop means the crop that is not keeping the soil open, and like peas and some crops are there which are like green manure crops. They get buried into the soil after the season. So the objective here was to understand how is the health of the crop and which are the regions where they can easily monitor the health progression across the season. So that was the objective. So I hope I have answered your question, or still it is not.
Sir, yeah, actually, if we take potato cultivation, there will be the color of the plant may be confused with other plants too. So how is it possible for us to separate both the plants? So that was my question.
Yeah. So see, that actually depends upon seasonality. So when we do the crop classification, as another person was also asking about knowing the potato crop, and also there was one question about another crop. So here, see, the potato will have certain cropping cycle. For example, major potato cultivation in India happens in Gujarat, some part of UP, and West Bengal. So these regions, when the potato is planted, there is a certain cycle duration, like certain months. Then when the potato will get planted, and during that time, what are the other crops that are present on the ground? So when we create training data, we take care of those crops, or we take them as also the crops that are alongside with potato, and those data sets are used in our training models, and we don't rely on only one satellite data. So we use time series of satellite data. Multiple time periods will give you separation between different crops. Like some crops which are still like green, looking like potato, like maybe onion and potato planted together nearby fields. One field is having potato, another field is having onion. They may look similar in satellite data because satellite is very far from Earth, around 700 kilometers. The issue here is, or the point here to understand is, onion may have its own cropping cycle, potato will have its own cropping cycle, and that separation can happen in temporal dimension. And that's how we separate the different crops. And that's how we separate the cotton from soybean, red gram from soybean, and cotton and red gram again between each other.
Okay, sir. Okay, I
Sir,
got it.
what may be the size of the field considered here, sir?
So here, this is very large field. This field that I'm showing as example is more than 100 hectares.
Okay, thank
More
you.
than 100 hectares. In
And also,
Indian
sir,
condition, potato cultivation, West Bengal geography, we have seen the field sizes are less than a half an acre. So there we need lot of training data for rice, potato, because rice and potato, they are cultivated in the same season in West Bengal geography.
okay, sir. Actually, you mentioned about the temporal revisit of satellites for Indian conditions, and may know which satellite could be openly available. That means the data is openly available to us for free. And
Sentinel-1, Sentinel-2, Landsat, Modis. In this Landsat, there are 2 satellites. Modis, there are 2 satellites. So these 4 satellite data sets are available openly across globe, across India, anywhere in the world, and any time in the world.
okay, sir. Okay, thank you.
Is there any other question from participant side?
Hello.
Yes.
Yeah. Thank you, Dr. Sivakant, for this informative session. So in the slides, I think you just mentioned about disease modeling and prediction. So can you hear me? Can you hear me?
Yeah, I can hear you. Yes.
Yeah.
That's good.
So, for example, is different monitoring stations in the field, are they sufficient enough to predict whether the crop is affected by disease, or do we need some information about, the spatial information from geospatial datasets or satellite datasets? So how far are just the monitoring stations are sufficient, or how do we integrate these two into this disease modeling?
Yeah, actually, you have brought a very right question in terms of disease modeling. So, see, disease modeling, there can be 2 ways of handling that over the macro scale and micro scale. When you are talking about is the field level, you definitely need sensors, at least temperature, humidity, and a leaf wetness sensor placed within the region of 2.5 kilometers or within that vicinity. That very dense network of sensors is required for doing very high precision estimation of this pest and diseases. But when we go for regional analysis, what we do is we used the data set or we use the data set that are fused. Fused means those which are generated from the global circulation models. Like I was showing on Earth Null School, the data set is typically 25-kilometer gridded data. And these data sets are fused by certain companies like there is Skymet, there are some other companies who have their own commercial rain gauge stations, and they uh, downscale that data set to a finer resolution like 9-kilometer or 5-kilometer spatial resolution, and then we use it for generating the macro level insights like village level insights or sub district level insights or forecasts for given pest and disease impact or pest and disease predictions. But that helps only for agri input companies, B2B sector. But as you
Yes.
were saying, if there is a farmer and who wants to know about very specifically for his or her field condition, then there is a definitely need of typical weather station or weather monitoring service within the vicinity of the field around 2 to 2.5 kilometer. And if it is again protected cultivation, like for example polyhouse or very high end cropping system like a vertical farming system, then definitely there is lot many sensors are required within the field itself. So that depends again. I may not have answered your question exactly, but that depends again on the scale that we are looking at and the financial equation that we are looking at. So
Yes,
whenever we are going for protected cultivation, definitely very high valued crop, very high end systems are required.
yes. Thank you. So one more thing I kind of gathered from this talk is that the domain knowledge and interactions with the farmers is very much required, I think, to modeling, whatever modeling or prediction we are doing. Is it? So with just,
Domain knowledge
yeah,
as such may not be needed, but if you have collaborator in agriculture university, these people they will be very open for collaboration. Like these days, agriculture universities are becoming bit open to technology colleges and technology schools. So what you can do is you can choose students because their students they are in and out in agriculture. So
correct.
like there are universities, agriculture universities nearby region or agriculture research stations, they are in and out in that particular field and farm. They understand the domain in a better way, and they definitely need help in terms of machine learning and AI based applications
Correct.
for their day-to-day problems.
Yes.
So combination of these two is definitely required in agriculture sector to at any level.
Yeah. Thank you. Thank you so much. Yeah.
Yeah.
And
Thank
Surya
you.
sir, you also showed some websites which will be useful for intern students. Could you please kindly share that links in the chat box, sir?
Yeah, I will share. I will share those. I'm just copying, pasting them.
Thank you, sir. Thank you, sir.
Yeah, maybe all of these resources can be shared together, I guess, once.
Yeah. We'll share all these slides with the participants after the completion of this FDP. We'll give you all the material session wise and we'll share on your register video.
Okay, sir.
Yeah,
Thank you, sir.
sir. Thank you. Sir has covered very deeply on the current trends in agriculture. What are the different challenges in agro-geo-informatics? And what are the business considerations? What are the challenges in B2B? Sir has given us the different data sources which are publicly available. There are n number of problem statements and open statements are there. So those who are attending this workshop, they are very much grateful to Dr. Suryakant sir. So they have a lot of things to work on these areas and you can give the problem statements to your students. Thank you very much, sir, for giving your valuable time and sharing your expert knowledge in the field of agro-geo-informatics. And we'll also thank on behalf of the Ramravadik Institute of Technology, D.Y. Patil deemed to be University, Navi Mumbai. And we'll be in touch with you in the coming workshop, in the coming STTPs in the near future. Thank you very much, sir.
Sir, is it possible to contact you if anything is required, Dr. Suryakanta sir?
Yeah. Feel free to contact at any point of time.
Yeah,
How
we'll
can we
share
contact
sir's
you?
email ID. Yeah.
My
We'll
mail
share
ID I have
sir's
shown.
email ID. And in fact, we'll share all the email IDs of all the speakers, those who have given their expert lecture in this particular online FTP.
Thank you so much, sir.
Yes. Thank you once again,
Thank
sir,
you, sir.
for your valuable time.
Thank you. It was nice to meet all. Thank you.
Yes. Thank you.
Sir, you're on.
Participants will join tomorrow for the day 3 lectures. There was a little bit swap of today's lecture. So don't worry. We have already shared the updated session schedule on the WhatsApp group. So be there for the new new lecture and with the new opportunities, new knowledge, new information. So be ready for the day 3 session, and please join with your registered email ID. If you are using your mobile phone to join the meeting, please log out from all the email IDs and just log into the registered email ID. Then there will not be any difficulty to join the workshop. Otherwise, it will be difficult to admit each and everyone in the meeting. So thank you very much, and we appreciate your cooperation throughout this activity. Thank you.
Thank you, sir. Thank you.